Okay, so we are going to start out with a demo. It's aimed right, hopefully. Well, first we'll have to do it that way. Okay, so I have a pumpkin here, and I'm gonna do 3 reactions. So the first thing I'm gonna do is I'm gonna put peroxide, hydrogen peroxide, into the pumpkin. Peroxide, as you know from earlier in the semester, will decompose to form water and oxygen, but it does so very slowly. So those of you who have a lab, you had to put the potassium iodide in there and then you would eventually see the bubbles. So we need a catalyst. It speeds up the reaction, participates in the reaction, but it isn't used up. You're using, if you're in lab, a catalyst in lab this week. So the catalyst we're going to use is an enzyme, which is a kind of protein, and it's found in pretty much all living things, but it's found in the pumpkin. And so I need to expose some more of the raw surface because the surface that's in there has already been reacted. That's why I'm scratching around in here. So that's going to get the catalase. And the catalase, as I said, is a catalyst that will help to decompose the peroxide. And I'm going to wear gloves because this peroxide is 30%, 10 times as strong as your regular household stuff. And if you get it on your skin, it is very, very painful. So take care of that. Then the second reaction that we're going to do involves calcium carbide. So I have that one written first. Don't ask me why I wrote them in the wrong order. I've been having a day. Okay, so the calcium carbide is a solid. And it's this way. See what I'm doing here. So I have just a small amount of that. I'm going to put it in addition. I'm not going to stick this in there just yet, but when I do put this in, I'm going to react it with water, and the water is going to produce calcium hydroxide. What can we tell me? Anybody tell me something about calcium hydroxide and its characteristics? What does the hydroxide tell you? It's a base. Yes, so this is a base. But the more important thing is we're making C2H2. And that is this chemical here. If you take organic chemistry, you will learn that this is acetylene. So if you've ever heard of an acetylene torch, welders might use an acetylene torch, or bakers actually use them to like brown the top of their special dishes or whatever. So we know that it burns, right? Now for fire, we need 3 things. We need the fuel, which is the acetylene. We need the oxygen, which is in the peroxide. What else do we need? 3 parts to make fire: fuel, oxygen, and why aren't your papers combusting? There's oxygen in this room. Your papers should burn. Why aren't they combusting? Heat. Yeah, we need an energy source, okay? So rather than, so you could use heat. We're going to use a spark. So you might be able to see a little blue flash here. Let me pull this down here. Let's let. So this is going to be our little spark. But when I put it through the hole in the back of the pumpkin, sometimes I get pumpkin guts on it. And since pumpkin guts are wet and water conducts electricity, I have to make sure that it still sparks when it's in here and it's not being short-circuited. So I don't want to do the acetylene before I check that because otherwise it would blow up in my face. So I don't like that. All right, so I am going to move this and hopefully we can get a little video of this. The second class, it made a little poof. I could see the fire, but pretty much nobody out there could see anything going on. So that was less interesting. So I have 2 pumpkins. If this one doesn't work, then we can try the second. Okay, this will be loud. So I'm going to put on earphones. And let's see, there's my graduated cylinder. So you may want to cover your ears. Give it a few seconds to build up a little bit. Okay. All right. 3, 2, 1. That is a self-carving pumpkin. Still hurting. Nice. I've never had that happen before. All right, so aside from it being Halloween, this does relate to our gas laws, right? Because we have some gases going on here. In our last reaction, we had acetylene gas and oxygen gas, and then those burn and produce these two gases. So I kind of described this in a problem that we did on, I think it was Monday, where we were talking about the temperature changing because there's fire in there. But I kind of simplified it because we're actually producing a gas here, we're producing a gas here, and then we're producing a gas here. Both of those will be gases at those high temperatures, but we're using up some gases. So if we increase the number of particles that are gases, do we increase the pressure or decrease the pressure? Increase, because there's going to be more collisions, right? And then the volume of the pumpkin pretty much stays the same, especially while it still has its carved pieces still in there. But the pressure is going to change. So the temperature goes up. I add more gases. What does the increase in the temperature do to the pressure? It increases the pressure, and so that combination creates enough pressure to have the pieces lie out here. So there you go, a self-carving pumpkin. Okay. So now we are going to go back to doing some calculations. If you have a calculator, I recommend you pull that out. I have a pencil calculator here. For sample problems, I do this because having a quiz over your content on a regular basis that you have immediate feedback on helps you to understand what you know and what don't you know. What don't you know? It's been shown that that's one of the best ways to learn. So my goal here is to help you learn. So that's the whole idea here. So please don't just stare at me while I do the calculation. Please try it out yourself. You will learn better if you do. It's the point of all that. First thing I want to do is look at kinetic molecular theory. We have talked about this in the past, but I don't think I've actually just said the words kinetic molecular theory. So I want to kind of get down what we're talking about with this. So we've talked about the idea that the observable properties of gases, like the volume, the temperature, and the pressure, can be related to the properties and the motions of the particles. We've said that before. That is kinetic molecular theory. And it has some assumptions about gases. So it's not just those properties, but also the idea that the molecules are very far apart from one another, and that they're moving very quickly. And those are going to set up what we call, those are going to lead us to a description of ideal gases. So ideal means not necessarily real, but in a perfect situation, this is what it would behave like. And we know nothing is perfect, but most gases behave pretty close to ideally under normal conditions. Okay, so usually they behave in such a way that how many particles, how many molecules or atoms are what influences the volume and the temperature and so on and so forth, not what the particles are. So it doesn't matter if it's helium or carbon dioxide or whatever. So when we say it doesn't matter what the gas is, we're saying it's behaving ideally. So why might this be the case? Because in a gas, particles are very far apart. And this has a couple of consequences. So we talked on Monday about how size doesn't really matter for gases. So the size of the particles themselves. And I use the example of us in the room. And if we were trying to have the area of us as opposed to a bunch of 2-year-olds. Well, for a gas, they're actually much farther apart than that relative to their size. So it'd be more like if the 25 of us were spread out all through campus. That kind of distance between us would be more like the distance of the gas particles. So they are so far apart that the size of the particle doesn't matter, but also the attractions that they have don't matter. So we talked about water being polar. Water molecules attract each other. They also attract ions. Other particles might be polar, or other particles might have some of these attractions, or maybe they're not attracted. Those should make differences, but because the particles are so far apart, they can't really feel those attractions. Just like if you're on the other side of a football stadium from somebody else, you can't really see whether or not they're attractive to you because they're so far away. The other thing that we talked about was that the gas particles are moving very, very rapidly. So if you think about driving along on a freeway at 70 miles an hour and somebody's coming in the other direction, 70 miles an hour, and they got their convertible top down. So you got a nice view of them as they pass by, just momentary though. Maybe they're super attractive and you want to go hang out with them. But at 70 miles an hour, like you'd have to get off at the exit, turn around and try and chase them down, and you don't know exactly what their car would be. And it's just not worth your time and effort, right? So even though you might momentarily say, hey, they're kind of cute, nothing's going to come, right? But if you are walking down the street and you and this other attractive person are walking along and you see one another, at that point, it doesn't take too much effort to say, how do you do? And try and get into a conversation with those people. So attractions matter more when you're going slowly, right? And so gas molecules moving fast means that they are not, that the attractions don't really matter. Okay. But this leads us to a description of when gases are ideal and when they're not. So when are gases not moving fast? When are those particles actually going slow? What would that describe? When it's cold. So gases, real gases, are going to behave ideally if it is a normal temperature, like our atmosphere temperature, to a very high temperature. And so by normal, think of anything you might expect for the weather. So, even 0 degrees Fahrenheit or negative 10 degrees Celsius or whatever. Those temperatures, they're cold to us, but to a gas, it's not a lot colder than it. But you get really, really cold, say liquid nitrogen temperatures. The temperature was so cold, the nitrogen started moving so slowly that they condensed into a liquid. They were no longer behaving like a gas at all, let alone an ideal gas. Okay, so ideal gas, high temperatures. Pressure has to be low, because if I have high pressure, then my molecules are really close together because they're all banging into one another and having lots of collisions, right? So if I have high pressure, then my assumption that the particles are really far apart isn't really true, okay? But at very low pressures, then that means my particles really are very far apart, okay? So normal conditions around 1 atmosphere, Yeah, that's normal. It starts to break down around doubling that, so around 2 atmospheres, but not enough for us to pay attention to. So normally we don't really worry about it, the pressure being too high unless it's like 10 times as much. So if you had 10 atmospheres, then you might say, no, that's not going to behave like an ideal gas. So if we think about in labs, sometimes you will see a cylinder that it's like this tall and it's got a pressure gauge on the top. It's holding a different kind of gas. So it might be oxygen, might be hydrogen. So those generally are pressurized. And if the pressure gauge is reading 22 atmospheres, would you expect that gas to be behaving ideally? No, because that's very high pressure. So it's going to behave, the real gas is going to behave, I wrote this way, I guess I should say ideally, at low pressures, not at high pressures. Okay, so questions about that? All right, so today and a couple of other times we've talked about several different aspects of this. These are kind of the key points to have. You need to know that in a gas, the particles are very spread out. And they're constantly moving. Now, the fact that it's random tells us that they're not collectively moving in one direction. If they were collectively moving in one direction, we would have wind. So in most, like in a room, it's not really moving in a direction. We don't have air currents. The collisions are elastic. That just means that when they run into each other, they don't slow down. So if you have two cars run into each other and then bounce off, they don't bounce off at 60 miles an hour because the car has crumpled and some of the energy has gone into that and they're pressing on the gas and all of that. Those would be inelastic collisions. So an elastic collision basically means that the average speed of those two particles stays the same.
I could just bring a game console, my master can in here, drive backwards on the track and show exactly that.
Right, but we're not going to do that. We don't need additional collisions. All right, and then we've also talked about the temperature is related to the speed. It's also related to kinetic energy, and we'll talk more about that later. But for right now, just think about how fast the molecules are going. And the pressure is related to the number of collisions. Okay, so that stuff there might be potential multiple choice questions that I might ask. I might ask you if I double the number of collisions in a gas, what am I changing? Am I changing the temperature? Am I changing the volume? Am I changing the pressure? And so you're going to think back and say, well, collisions, that has to do with pressure. So that's probably what you're changing, is the pressure. All right, anybody still need this? Okay. So we also have been doing some conversions with different temperature or pressures. And I'm not going to go through each of these line by line because you've seen them before, but this is one I want to point out. It's a pretty simple one. Anybody know the answer to this one? Yes, it's the same thing because remember, a millimeter of mercury is just another way of saying a torr. Okay. So that's good to remember on your quiz. If I write this many torr and you're thinking millimeters of mercury, they're the same thing. Okay. I won't ask you to convert that. So if you go and look on Canvas at this slideshow, you will see this problem. You can check it out for yourself and a few others, but I'm not going to pause them right now and do those because we've done lots of pressure conversions. All right, another thing that we've talked about is being able to identify which equation to use. So suppose you have a question like this. We have a syringe is placed in a stoppered vial. So this is a vial, a little cylinder. We put the syringe on top so it's sealed. And then we pull out the plunger just like you did on the micro apparatus. And so this was 15 milliliters. And then as we pull that out, we add 10 more milliliters. Okay. Initially, we were at 1 bar. And if we're trying to find the new pressure, we've got to pick an equation. Which equation is going to be helpful? Why?
That's two different volumes.
Yeah, we have two different volumes. We're changing our conditions. So I have these things here. If you wanted to add this to your extra credit thing, I find this kind of handy when I'm in a situation like this, because we have different volumes. We know we have different pressures, but we don't have the temperature change. So what do you do with this? You look at, when you have it like this, you look at whatever is not changing and you cover it up. So this down here says if you have constant temperature, cover T. Now this is our equation. Okay. Now, if I were doing a question with the volume of our pumpkin not changing, I would cover up the V's, and now that's the equation that I would use. Okay, so this is kind of a helpful tool for helping you use the combined gas law when something is constant. Okay. Oh, and I forgot to change this. Sorry. All right, so we said that we are going to use the combined gas law. Now I'm going to have you try and figure out the answer to this question, and you all have, you should have whiteboards at your desks. All right, and this one actually has some multiple choice options. So remember that this is basically what we're looking at. P1, V1 is equal to P2, V2. All right. Okay. Now this does have a little bit of a trick in it. So one thing you might think about as you're coming up with your answer is, if I have an increase in volume, it says the volume is increasing by 10 milliliters, what should happen with the pressure? Volume goes up, pressure should go down. They are inversely proportional. Okay? So could eliminate some of the choices just based on that information. The question is, you have to come up with a number. How do you do that? Yep. So what's my initial volume? V1. 15 milliliters. What's my final volume? It is 25. It is the sum of the 10 milliliters and the 15 milliliters. Okay. So if you got, yes, if you got something that is going up, you probably were using just the 10 milliliters. But remember that volume from the original vial, that's still there. We just added 10 milliliters on top of it. Ready? So I have about 4 people that have given me an answer. Anybody else got an answer? Yep. Okay, but I want you to write it down so you're not telling everybody else. Okay, so we should have ended up with 0.6. So what do? You take your 15 V1 times 1 bar P1, and then you'll divide by the 25, which is the sum of those two. So 15 divided by 25 gives you the 0.6. Okay. This is another one I'm not going to go through, but I did want to point out, if you go and find this on Canvas, you will see this question. And then I have given you how to set it up and what the answer is so you can check yourself. So don't just read through it. Try and do that calculation yourself before you look at the final slide. And if you're finding that you need to look at the final slide to get to the answer, that's an indication that you probably need a little more practice before your quiz. Okay, we also talked about density on Monday. And we said density is mass divided by volume. And if we have 1 mole, then the mass is the molar weight. And if we have 1 mole, the volume is what we call the molar volume. So this little m here, molar. And that essentially is the same thing as when I wrote 1.00. It's just saying I have 1 mole. Okay, so it's per 1 mole. All right, so we found density the other day, and we said that if we wanted the molar volume at STP, that would be 22.4. So first of all, what does STP stand for? Standard temperature and pressure. So what is standard temperature? 0 what? Celsius. So that would be 273 Kelvin. And standard pressure is 1 atmosphere, okay? But we're not always at those conditions. It is, thank goodness, not 0 degrees Celsius in here. So what happens when we're at a different temperature? You have to recalculate what that molar volume is if you're going to use this formula. So you just take the ideal gas law and rearrange it for the volume. Okay, so the volume is going to be nRT over P. And since we're finding the molar volume, N is going to be 1. And this morning, it was 20.7 degrees in the lab, and the barometer was reading 737 millimeters of mercury. It's changed slightly since then. So I want you to try plugging those numbers in and putting that on your whiteboard. So make sure your temperature is in Kelvin and your pressure is in atmospheres before you start plugging into the ideal gas law. We are changing the temperature and pressure, but not by a whole lot. 0.97 isn't real far from 1, right? So you should expect something near 22.4, but it's not going to be exactly 22.4. That should help you know if you're getting a good answer. So you should end up with 24.85, but we got to round this to 3 significant figures. Technically, the rule is to round to the even number, which would be 0.8. But in practice, it doesn't really matter which way you do it. You're just supposed to round half of the time up, half of the time down. So if you said 24.9, I told you that was correct. Okay, so now let's move on. What if we want to know what the identity of a gas is? So the identity of gas doesn't affect pressure or volume or temperature, but it does affect the mass. So we can use the mass to determine the identity of the gas. And in particular, the molar mass is what's going to be helpful to us. So we can take our equations that have a molar mass, like the density equation we're looking at, and we can solve for the molar weight. Okay. So if I just take the ideal gas law and turn it around and solve for moles, then I end up with mass divided by moles, or mass times RT over P. That would give you your molar weight. But sometimes you're going to be given density. And I'm going to do a problem that involves that. So we'd rearrange that density equation. So density was molar weight over molar volume. So I'm going to multiply both sides by molar volume. So molar weight is density times molar volume. So remember, molar volume means 1 mole. So N doesn't appear in this formula because I'm assuming that I have 1 mole. And I'm substituting this for the volume. All right. So the molar rate is the density times RT over P. Okay. So these two equations are the two that are good for finding molar weight, depending on whether you were given the mass or given the density. So like I said, we're going to go through a problem that involves the density here in just a second. All right, anybody still need this slide? Okay, so let's say we have a certain noble gas at 20.7 degrees Celsius and 737 torr. So these are the same numbers we used before. That way we didn't have to do a new conversion. But remember, we do have to have Kelvin. We do have to have acid. So this noble gas has a density of 0.810 grams per liter. And we want to know what the identity is. So we're going to find the identity through the molar mass. And so we have our formula, the second one on that page. Molar weight is density times nRT over P. And I should have left the N out because that's 1. So anytime density is involved, just assume 1 mole. And then we said that the temperature in Kelvin was 293.8. I got there by adding my 273. And the pressure was 0.970 atmospheres. I got there by dividing by 760. All right, so find for me what is the molar mass. And then see if you can figure out what the identity of the gas is. There you go. Okay, so you should have come up with a mass of 20.1 grams per mole. So what's the identity of that? How are we going to find that? Periodic table. So what element has a mass of 20.1?
Neon.
Neon. Now, we have another clue in here that says it is a noble gas. Is neon a noble gas? Yeah, so that's further verification that yes, we probably have the right answer. Okay, this slideshow also has a stoichiometry problem on it. We've done one stoichiometry problem before. I'll try to go through this at the beginning of class on Friday so that you have a chance to see it, but you may want to take a look at it before Friday because you may see stoichiometry. One more thing about your quiz. I decided that since you can use a 3x5 note card on your test, I'm going to let you use that on your quiz. I will give you the equation. So good thing to put on the card is when do I use the combined gas law? When do I use ideal gas law? What do I assume about moles if there is a density involved? Okay. All right. So that's all I got for you. Have a good day.